Good morning. We are continuing with Faraday's law, Lenz's law, looking at various circuits where we did two last time, and we're going to do a couple of more today and just keep making them a little more interesting, a little more complicated each time. All right. And then we'll have our have a review session at 2 o'clock if you're able to make that. I can post the notes in the lecture notes section. Okay, so let's start off with another one of those problems. Changing magnetic flux induces an EMF, causes current to flow. That's what we're doing right now. All right, we've got a circuit that consists of these rails. We can conductive rails. We can slide a conductor along it. And our magnetic field is being caused by a wire over here. Okay. What direction is the magnetic field in our loop of wire? Out of the page on the left. And into the page on the right. Okay, is there any current in this circuit? Any induced EMF? Is anything changing? Nothing is changing. Let's do it anyway. Okay, we know the answer has to be 0, so let's just see what we get. So let's just, I'll ignore the signs for now. The only time you need to take the sign into account is if you have multiple changes all happening at once. Some of them might be causing the EMF in one direction, some might be causing it in the other direction. When will we have that? In the next example. Okay, one thing at a time. I like to just write this out every time. N is 1, right? We only have one loop of wire here. N is 1. So d flux dt, that's what I'm looking at here. I always like to write this out. The flux is the integral of b dot dA. Then once I've written that out, then I ask myself, is the magnetic field constant over the area? If it is, this integral is just b times A. Is the magnetic field constant over the area?
No.
No. No. Because it's being caused by a current carrying wire. So as we move away from that wire, the magnetic field drops off as 1 over R. The magnetic field over here at this end is less than the magnetic field over here at this end. The magnetic field is not the same everywhere over the area of that loop. So we have to do this integral. We can't just say it's b dot dA, it's b times A. We actually have to do the integral. All right, let's do it. So this is the integral of B. What is the magnetic field from a current carrying wire? You can use Ampere's law and derive that in a couple of lines, right? Or you can use Biot-Savart law and derive that in a little bit longer. Either way. That's the magnetic field from a current carrying wire. dA, let's see. What are we going to choose for our area element? We could choose a small rectangle there, have a dx and a dy, call that dA. But our magnetic field is only changing in one direction. So I have to have, in the direction the magnetic field is changing, I have to have a tiny, tiny little section, right, of my area, because what am I assuming? I'm assuming it's not, the magnetic field is constant over that region, right? So I'm going to pick this as my dA. This is dr. And this is, what is this? W? I think I'm calling that W. Forgot. W. And then I think this distance is X. Oh, I've got X's for everything over here. Here, I'll put these in little circles. The magnetic field here is into the page. How's that? And this is X is my distance. So this is W over here. Okay, R is the distance from the wire to where we want to know what the magnetic field is, right? Our point of interest. This R right here. The magnetic field drops off as 1 over R as we move away from the wire. And so the distance away from the wire is R, that's what we're calling R. And dr is a tiny, tiny little change in that distance. And if we assume that over that tiny, tiny little change, the magnetic field is constant, then we can do this integral, right? But B does not change along the length of the wire. So that can be as long as we want. B is constant over the length of the wire. Okay, so where are we? W dr, that's my dA. And what am I integrating from? A to A plus X over the area of the loop. This area right here. Right? That area right there. Okay, A to A plus X. So I can do that integral. I still have this d dt out here waiting for the next step, but that's okay. I'll deal with that when I get there. Mu is constant. I, W, 2 pi, those are all constants. I have an integral of dr over r. All my constants are still there. And the integral of 1 over r is the natural log of r. And that's the natural log of a plus x minus the natural log of a, which is the same as the natural log of a plus x over a. Okay, now we're done with the with that part, with the flux part. Now we're ready to look at the change in time. So is anything here changing in time? Is A changing in time? No, the loop doesn't move. Is X changing in time? No, the velocity is 0. Is the current changing in time? No, nothing's changing in time. Everything here is constant. In time. So we get 0. All right. But I thought that it was important to do one where the magnetic field was not constant over the area of the loop. And we had to integrate to find the flux. We good with that one? Both parts work. What does that mean? Oh, yes. Yeah, this one you hopefully spotted right from the beginning, most of you did, right from the beginning that there's nothing changing. The induced EMF had to be 0. But the math has to give you the same answer too, right? The math has to work also. But the important point here was that the magnetic field was not uniform over the area. We had to integrate to find the flux. So I could have had something changing here, right? I could have made this current. I could have made that current I naught. Why isn't it red? I could have made that current some function of time, alpha t squared, right? I could have made that current a function of time. Then the magnetic flux would be changing, right? I could have made a function of time. I could have had the whole loop moving with some velocity, right? So A was changing. That would have induced an EMF because the whole loop would be moving to a region with less magnetic field because the field drops off as you move away. Okay, I could have had this bar moving one way or the other. We could have changed any number of things, right? In this case, nothing was changing. Okay, but that just affects this last step, the time rate of change. Okay, let's do another one. We're going to combine problems 1 and 2. So we've got a I'm going to have it moving in this direction. V, and then we've got a magnetic field coming out of the page. And B is going to be a function of time. So we've got two things changing simultaneously. So can you come up with an equivalent circuit? So what would an increasing magnetic field do here if the magnetic field is increasing the way it is here, right? It's a function of time. As time goes on, the magnetic field gets bigger and bigger and bigger out of the page. That would cause current in which direction? Shoot. Which direction?
Isn't that also depends on the velocity of that rod?
Yeah, we're ignoring the velocity, one thing at a time. Just the magnetic field. What's it doing? As the magnetic flux increases, out of the page like this. A current would get set up to create its own flux into the page. So it would be going clockwise. So that means that I could put a battery over here, right? In this orientation. And this would be for the B increasing, right? We good with that? Now, if we ignore the magnetic field changing and just look at the velocity of the bar, what would that be doing? It would be decreasing the flux, so current would get set up to try to increase the flux. It would get set up counterclockwise. We good with that? So I could draw a battery over here and call that E velocity. So we've got a fighting, competing EMFs here. One of the things that's changing, the motion of this bar, the velocity of the bar, would cause current in the counterclockwise direction, or a battery oriented the way I've drawn it. The other change, the increasing magnetic flux, would cause current in the opposite direction, or a battery like I've drawn it. So they're going to, so in the end, of course, in the end, we'll draw this circuit with one battery, but we need to figure out what that voltage is going to be. All right, so let's find out what voltage and what orientation it would be. All right, so I asked myself, is B constant over the area? Is B constant over the area?
Nope.
Constant over the area. The answer is yes. If we could freeze time for a second and we ran around that loop with our magnetic field sensor, we would measure the same magnetic field everywhere within the region of that loop, everywhere over the area of that loop. Then we let time roll forward a little bit. The magnetic field gets stronger and stronger and stronger. And then we freeze time and run around and check the magnetic field everywhere in that loop. It's the same everywhere in that loop. The magnetic field is constant over the area. It's changing in time, but it's constant over the area. So this integral just becomes B times A. So is the magnetic field changing in time? Yes. Is the area changing in time? Yes. What do we do? Product rule, right? This is going to be B times dA dt. And this is going to be A times dB dt. Now, actually, I'm going to One thing we have to be careful of, though, the area is getting smaller in time, right? This is a negative number. The magnetic flux is getting bigger in time. That's a positive number. Okay, we have to be careful of our signs here because they're going in opposite directions. If they were all going in the same direction, if both of these were oriented the same way, we could ignore the signs completely, right? We know what direction they're going. All right, let's do that. So what do we get for the okay, so we've got a B, which is alpha t squared, and a dA dt, which is minus W dx dt. And we have an A, which is Wx. And we have a dB dt, which is 2 alpha t. Is that right? And I get something like dx dt is just the velocity. Something like that. And this tells you which one's going to win here, right? So the changing area, that's this one, right? This is due to the changing, this is changing A. So if that one dominates, if this one wins, then we know that the current is counterclockwise. If the other one wins, if the other one's bigger, then we know it's clockwise. Okay. I have to give you numbers. I didn't give you any numbers. Yes. The one that produces the larger EMF wins. I see. I can change that. Let's see. Okay. All right. Let's see. Let's do this one. And then this is going to be this one's going to be able to slide back and forth. Let me draw it just a little differently. And this one can slide back and forth. Okay, this will be moving this way, 4 meters per second. This will be moving that way at 2 meters per second. This is a 10 ohm. This is a 5 ohm. 10, 5, 15. What else do we need? 10 centimeters. Let this be W. And we need a magnetic field, don't we? B will be into the page. And it will be 0.01 Tesla. You got an equivalent circuit yet? Yes. All right, so the moving 10 ohm resistor creates an EMF on that side that's like a battery. I'll call it battery 1, EMF 1, in this orientation. And the moving 15 ohm resistor creates an EMF that's like a battery in this orientation. Now we use Faraday's law. And the magnetic field is constant over the area. So this is just the flux becomes B times A. And the magnetic field is constant in time. So this is just d dt of the area. And the length doesn't change. And that is just the velocity. And you do the exact same thing for the other battery. This one ends up being 4 millivolts, and the other one is 2 millivolts. I just plugged in the numbers here. Magnetic field times the length times the velocity. I gave you numbers for this problem. I know I don't usually give you numbers, do I? But I gave you numbers for this one. So we pick our directions, quick review of Kirchhoff's. I'll just guess there that the batteries are pushing the current in those directions. And then we get 2 loops. Okay, be careful of your units. You probably want to convert those to volts. Okay. Time for one more. Let's do that problem where the with the current carrying wire generating the magnetic field in our loop. So our magnetic field changes over the area, but let's have the current change in time. So we've got this set up. And a loop of wire over here. This is A and B and C. Okay, I is a function of time. Think about that for a minute. In what direction would the current be generated in that loop? Because the magnetic field is into the page and it's getting stronger and stronger and stronger. So a current gets set up to try to subtract from that flux to make it weaker again. All right, let's find the value of the EMF. Are you doing that? All right, and we ask ourselves, is B constant over the area? And the answer is no, it is not. So we have to integrate. We have to do this integral. So let's just leave our d dt out here for now. We'll come back to that later. And we're going to do this integral. What is B? It's mu naught I over 2 pi r. Use Ampere's law to get that. What is our dA here? That's it right there, right? So if this distance is r, this would be dr. So C times dr would be dA, the area of that little thin sliver. That means that I come down here and I put C dr here. And what am I integrating over? Integrating over the area of my loop, right? This area right here. The area of this loop. So that means R goes from A to A plus B. A to A plus B. And what do I get? D dt mu naught I C over 2 pi. Those are all my constants. I've got an integral A to A plus B of 1 over R dr. That's going to be the natural log of R. That's the natural log of A plus B over A. And then I say, what's changing in time? The only thing here that's changing in time, mu naught and C are constants. 2 pi is a constant. The natural log of A plus B over A is a constant. The only thing that's changing in time is the current. And I can plug that in, right? di dt is equal to d dt of 2t plus 3 is equal to 2. Okay. Good stuff. So that should give you a lot to think about this weekend. Practice with these different things changing. So remember, a changing flux, right? A changing flux is what is causing this. Flux is the integral B dot dA. So what could cause the change? A changing B field. What could cause the change? A changing area. What else could cause the change? The orientation between the two changing. Any one of those three things changing will cause an induced EMF. Review today, 2 o'clock, right? Otherwise, enjoy your weekend. I can't stick around right now. I've got a class coming up. Okay? Have a good weekend.